Hey everyone, and welcome to this explainer. Today, we're going to dive deep into the completely fascinating, invisible atomic reasons why some materials easily power our modern devices, while others stop electricity completely dead in its tracks. We'll be exploring the principles of band theory and electrical conductivity, and I promise you, by the end of this, you're going to look at the electronics sitting right around you in a totally new light. So let's kick things off with a really simple question about the stuff we interact with literally every single day. Think about your standard phone charging cable. You've got a metal wire on the inside, usually copper, right? And then a rubber or plastic coating on the outside. Now, the copper carries the current perfectly, but the rubber completely blocks it from shocking your hand. But why? What is physically happening on a tiny, atomic level that makes these two materials behave so radically differently?
Well, nature basically sorts everything into three main buckets based on how well they conduct electricity. Over on one side, we have insulators. On the complete opposite side, we have conductors. And then sitting right there perfectly in the middle, we have semiconductors. This very simple categorization is actually the entire foundation of modern electronics. Here's our roadmap for today's explainer. We'll cover 1. The conductor continuum. 2. Unlocking band theory. 3. Mind the band gap. 4. Heat and electrical flow. And finally, 5. Doping, controlling the current. Let's get right to it.
Section 1. The conductor continuum, exploring the materials that shape our world.
The absolute crucial point to understand here is that materials exist on a spectrum, from freely allowing electrons to move to completely blocking them. Conductors, like copper, silver, or gold, offer a super generous flow of charge with almost zero resistance. On the other extreme, we've got insulators like rubber, glass, or quartz. These offer incredibly high resistivity. We're talking in the order of 10 to the 10th up to 10 to the 12th ohm centimeters. It's a massive, massive barrier. But then, right in the balance, we have our semiconductors, most famously silicon and germanium. Their conductivity falls exactly in the middle.
Section 2. Unlocking band theory, diving into the quantum realm.
Now, to truly understand why these materials behave this way, we have to zoom way, way in. When you look at a solid chunk of metal, you don't just have one or two atoms. You have an unimaginably huge number, more than 10 to the 24th power of interacting atomic orbitals. When these billions of orbitals pack so tightly together, their individual energy levels kind of blur together. They generate a continuous set of allowed energy levels that we call bands.
Within this theory, there are two primary bands we really care about. Think of the valence band kind of like a crowded parking lot where electrons are securely bound to their atoms. At absolute zero temperature, this is where they're all stuck. But just above that is the conduction band, which is essentially an open highway. If those parked electrons can somehow get up into this vacant band, they are finally free to accelerate and zip across the material, carrying an electrical current. Section 3. Mind the band gap, the toll booth for electrons. So between that crowded parking lot of the valence band and the open highway of the conduction band lies what we call the forbidden band gap. This is the actual physical jump in energy that electrons have to make, and its size dictates literally everything about a material's electrical behavior. For conductors, there is no gap. The bands actually overlap, so electrons are already on the highway. For insulators, that gap is massive, greater than 5 electron volts. Electrons just simply don't have the energy to cross it. But semiconductors, that's where the magic happens. They have a very small band gap, about 1 electron volt. At absolute zero, they act like insulators, sure. But if you give those electrons just a little push, they can jump right across. Section 4. Heat and electrical flow, the temperature paradox. Now, here is a real surprise. If you measure resistance against temperature, you find that as a metal heats up, its resistance actually goes up. It gets worse at conducting. But for semiconductors, as temperature increases, the resistance dramatically drops. Its conductivity absolutely skyrockets. So why does heat make a metal worse at conducting, but a semiconductor so much better? Well, for semiconductors, thermal energy acts as that perfect little push we just talked about. Remember that small 1 electron volt band gap? When you heat up a semiconductor like silicon, that thermal energy promotes electrons straight out of the valence band, right across the band gap and into the conduction band so they can start conducting electricity. The crucial takeaway is this. Heat creates a traffic jam in metals, but it opens up brand new express lanes in semiconductors. See, in a metal, the electrons are already on the highway, so when you add heat, the metal's nuclei just vibrate more rapidly in place.
The moving electrons end up crashing into these vibrating nuclei over and over, slowing down the whole current. But in a semiconductor, you are actively giving electrons the kinetic energy they desperately need to jump up to the conduction band. You're literally creating more active charge carriers.
Section 5. Doping. Controlling the current.
And this brings us to a real game changer, doping. Because if heat can change conductivity, what if we manipulated the atomic structure itself? By deliberately injecting tiny intentional impurities into a pure semiconductor, we don't have to rely on unpredictable temperatures. We can permanently and manually dial in exactly how well a piece of silicon conducts electricity.
There are basically two ways engineers do this. If you dope silicon with a group 15 element like phosphorus, you're adding an impurity that has an extra valence electron. This creates an N-type semiconductor, where N just stands for negative. These extra electrons sit right below the conduction band and easily hop up to carry current. Alternatively, you can dope it with a group 13 element like boron to create a P-type semiconductor. This creates missing electrons, literally positive holes, in the valence band. An adjacent electron can slide into this hole, which leaves a new hole behind it, allowing current to flow in this really cool atomic bucket brigade mechanism. Basically, you add extra electrons or you add holes for electrons to fall into, giving us total mastery over how electricity moves.
The ultimate result of controlling these energy bands and doping silicon is absolutely mind-blowing. We can make microscopic switches. By mixing these N-type and P-type materials together, we don't just conduct electricity anymore, we completely control it. We create the microscopic transistors inside your smartphone, your computer, and the very servers hosting this explainer. And get this, tens of billions of them can fit into a single square centimeter. And it all functions perfectly, just because we understand the principles of band theory.
So we've journeyed all the way from the rubber and copper wire in your hand straight down into the quantum interactions of billions of atoms. It really makes you wonder, doesn't it? As we continue to master the band gap and push the very limits of materials science, what new materials are we going to discover next? How is the ongoing manipulation of the quantum world going to shape our future technology? Thank you so much for joining me on this deep dive. And as always, keep questioning the science behind the everyday objects around you.